All right, today we're talking about increasing and decreasing functions. Starting with definitions, if f is a function defined on an interval I, f is increasing if for every a less than b in the interval, f of a, the function value, is less than f of b, the function value for b. It's the opposite for decreasing. F is decreasing if for every a less than b, then f of a is greater than f of b. Now, informally, what this means is that a function is increasing if as x gets larger, meaning we move from left to right along the number line, f gets larger, and decreasing if when we move from left to right on the number line, f of x gets smaller, so it goes down. All right, we're going to look at some examples here, and this is a place where you guys need to work along with me. You're going to have table of values for 4 different functions. The points have been plotted. You're going to sketch the tangent line at each point. You're going to do that using the values of the slope that is given in the table, the value of the derivative. We're going to use the points and the tangent lines that we sketched to sketch a graph of the function. And then we're going to answer these questions. We're going to talk about whether the derivative is positive or negative. We can figure that out from the table of values. We're going to figure out if the function is increasing or decreasing. Again, we could figure that out from the table of values, but it's easy to see from the graph as well once we've got that sketched. And then we're going to figure out whether the derivative is increasing or decreasing. Again, we can look at the table of values for that. All right, first example, we've got our points plotted. And just again, a reminder about sketching the tangent lines. I'm going to start at 0, 0. The slope, which is from the derivative, is 0. So that's a horizontal tangent line there. At the point 1, 1, the slope will be 2. So that means if we move over by 1 unit, we should be going up by 2. So we should have a tangent line that goes about like that. And then similarly for our other points, and when we sketch the tangent lines, we should get something that looks like this, roughly. And then from that, we see that we can go ahead and sketch a graph just following along those tangent lines. And when we do that, we get something that looks kind of like this. Now, continuing on to answer the questions about the derivative and the function. The derivative we see from our table is positive. We're going to ignore that 0 in there. The function we can see from the table, but also from our sketch, is increasing. And the derivative also, if we look at the values of our derivative, those are also increasing because they're getting larger as it goes through the table. All right, next function. Points have been plotted. Again, just a reminder about using the values of the slope. Those are our derivative values to sketch the tangent line. For example, at 1, 1, the slope is 0.5. So when we move over by 1 unit, we're going up by half a unit. So it's going to be something kind of like this. So when we get our tangent line sketched, it should look something along these lines. And again, we can see that we should be able to sketch a graph just going along the edge of that. And we get something that looks like this. And now we're going to answer the questions about the derivative and the function. For the derivative is positive. We see that from our table of values. The function, if we look at our table of values and also our sketch, we can see is increasing because when we move from left to right on the x-axis, the values of the function are going up. And then our derivative, if we look at the table of values here, our derivative is decreasing because those values are getting smaller as we go through. All right, next example. This time we have some negative values for the derivative. So we're going to have negative slopes for the tangent lines. And right here at 1, 1, our slope is -1. So if we move over by 1, we're going to move down by 1. So we're going to have something that looks kind of like this as our tangent line. And when we sketch all of those tangent lines, we're going to get something along these lines. And we can sketch in a graph that should look something like this. And now we're going to answer our questions about the derivative and the functions. So the derivative is all negative values here. We see that from the table. The function we can see from the graph and also from the table is decreasing. And then the derivative, if we look at these values, the derivative is actually increasing here, because if we look at the values, -1, -1/4, -1/9, -1/16, -1/25, that is moving from left to right on the number line. So that is increasing. Okay, and our last example here, this time we have some negative values for both the function and the derivative. But again, just a reminder, at 0, 0, the slope is 0, so we're going to have a horizontal tangent line. And then at our next point, 0, -0.13, our slope is -0.75, so it's going to go something along like that. And then we also get some much steeper negative slopes this time than we've seen on other examples. When we sketch the tangent lines in, we should get something that looks kind of like this. And then when we sketch in the graph, we should get something along these lines. So the derivative, looking at the table, and again, we're going to ignore that one spot where the derivative is actually 0. The derivative is negative. The function is decreasing. And the derivative is also decreasing because the values of the derivative are getting more negative as we go. So if we put these on the number line, we would be going from right to left. So those are all decreasing there. Okay, some observations. What we should see happening here is that when the derivative is positive, the function was increasing. And when the derivative was negative, the function is decreasing. And a function can be increasing, and the derivative can be either increasing or decreasing. And the same thing for a decreasing function, the derivative could be either increasing or decreasing. Now, when the derivative is increasing, one thing we can notice is that the graph is above the tangent lines. We're going to go look at this example here. And in the slides, if you click that button, you can jump back as well. So here you see the tangent lines are lying below the graph. And when the derivative is decreasing, the graph is below the tangent lines. So we're going to go back and see an example here. So decreasing, the graph is sitting below those tangent lines. Okay, so now we come to the increasing-decreasing test, which says that f is continuous and differentiable. We have to be able to find the derivative. That's what differentiable means. If the derivative is positive, f prime of c is greater than 0 in the interval, then f is increasing on the interval. If the derivative is negative, less than 0 on that interval, then the function is decreasing. And if it's always 0 on that interval, then the function is constant. And we're going to apply the increasing-decreasing test in order to figure out what happens with the graph of a function if what we know is the definition of the function. But first, we're going to look at a couple of examples. For the function f given in this graph, we're going to figure out where the function is increasing and where it's decreasing. So when we look, this is easy to tell. Increasing along here because the graph is going up, decreasing along here, increasing again, and then decreasing. So our intervals where the function is increasing, we're going to say it starts at -infinity. We don't actually know that, but we'll just make that assumption this time. So we're going to go -infinity to -1. And then again, from 0 to 1, the function is increasing. And for decreasing, that's from -1 to 0. And then from 1 to infinity. Again, we're going to pretend we know this just continues on. Okay, next example. This time we have the graph of the derivative of the function. And we're going to use the graph to determine where f is increasing and decreasing. So remember, this is the graph of the derivative. We're figuring this out for f. Well, according to the increasing-decreasing test, when the derivative is positive, which in this case means above the x-axis, then the function is increasing. And when the derivative is negative, meaning below the x-axis, when we're looking at the graph, then the function is decreasing. All right, so f prime is above the x-axis between -2 and -1, and then again above the x-axis from 2 onward. So for the intervals where the function is increasing, that's going to be -2 to -1, and then 2 to infinity. For decreasing, that is when the derivative is negative. So that means that's going to be where the function is below, where the derivative function is below the x-axis. So it's going to be up to -2, and then between -1 and 0. And right at 0, it's at 0. So we're not going to include that. But then from 0 to 2, the derivative is negative. So that means the function is decreasing. So from -infinity to -2, from -1 to 0, and then 0 to 2, the graph of the derivative is below the x-axis, which means f prime is negative, less than 0, which means f is decreasing. Okay, this brings us to the key idea, which is about finding intervals for when f is increasing and decreasing. Here's what we do. We find the critical values of f. And remember, that's where the derivative is 0 or not defined. We use the critical values to split up the number line, or if we just have an interval, the interval, into subintervals. We pick any point in the subinterval. We find the sign of f prime of p, that point p. So that means we're looking for whether it's positive or negative. If f prime of p is positive, then f is increasing. If f prime of p is negative, then f is decreasing. We're going to keep using this key idea over and over again in examples. Okay, we're going to find where f of x equal 3x to the 4th minus 4x cubed minus 12x squared plus 5 is increasing and where it is decreasing. Now, you should pause here, follow the link down here to the YouTube video for this example. There's also a link in Blackboard for the playlist for these examples. But for now, okay, so continuing with the first derivative test. So the first derivative test tells us where we get a local max or local min, if any, and it uses the ideas of the increasing decreasing test. And what we see is that if f prime changes from positive to negative, then f has a local max. Remember, if f prime is positive, that means that the function is increasing. And if the function is, if the derivative is negative, then that means the function is decreasing. If f prime changes from negative to positive, we get a local min. And so that means if f prime is negative, then the function is decreasing. And if f prime is positive, that means the function is increasing. And so you can see from the arrows, it sort of suggests a max, a high point, a min is a low point. But if f prime does not change sign, then f has no local max or local min at C. All right, we're going to do an example. We're going to find the local max and local min of f of x equal 3x to the 4th minus 4x cubed minus 12x squared plus 5. Familiar function. We just figured out the intervals where this was increasing and decreasing. So this next part will be really easy to do. And you should pause here, follow the link to the YouTube video, or use the link in Blackboard. And next, we're going to find the local max and local min of f of x equal x times the square root of 6 minus x. And again, pause, follow the link, watch the video for the explanation there. And then finally, we have our last example. We're given the graph of f prime of a continuous function f. We're going to figure out the intervals where f is increasing and decreasing. We're going to figure out the critical numbers, and we're going to find any local max or local min values. Now, for increasing, the function f is increasing if the graph of the derivative is positive, is above the x-axis. So we're looking for intervals of increasing. That's going to be where f prime is above the x-axis, and that's in 3 places there. from 0 to 2, from 4 to 6, and then 8 to 9, and we're just going to cut this one off at 9. The function f will be decreasing if the graph of the derivative is negative, if it's below the x-axis. So that's going to be between 2 and 4, and then from 6 to 8. So the intervals where f is decreasing are 2 to 4, and then 6 to 8. Now, critical numbers, remember that critical numbers happen where the derivative is either 0 or the derivative is undefined. It doesn't exist. So when we look at the graph of f prime, we're looking for where that crosses the x-axis. So that's at 2 and at 4 and at 8. But also at x equals 6, we see that the derivative is not defined because we've got this break in the graph and holes there. So our critical numbers are 2, 4, 6, and 8. Now, for a local max, that is going to be where the function switches from increasing to decreasing, which means that the derivative is going to switch from positive to negative. All right. All right, for the local max, that we're looking at where the derivative switches from increasing to decreasing. So that will happen at x equal 2. And then if we look again here, we're increasing, we're looking to switch to decreasing. So that would happen at x equals 6. For a local min, so our local max is x equal 2 and x equals 6. For local min, that would be where we switch from decreasing to increasing. So that happens at 4 and then also at 8. So we would have a local min at x equal 4 and x equal 8.